Good morning. I'm excited to share our lab's latest efforts in leveraging AI to tackle some important and complex challenges with the ultimate goal of bringing these technologies to clinical practice. Over the past few years, we've focused not just on cutting edge research, but also on real world translation. I think that's important to us because developing sophisticated AI models isn't enough. What really matters is whether they solve problems that clinicians face every day. To do that, we started by understanding the clinical need. We work closely with experts to pinpoint the real challenges, then go back to the drawing board to innovate on AI. The goal is to sort of really bring or create these solutions that aren't just technically impressive, but are also practical, reliable, and something, hopefully the end users really want to use. Uh, of course, making this happen takes, more than just great algorithms. It takes a team, and that's what makes our work so exciting. Um, And this is my team. I'm very proud to say this because our lab is truly multidisciplinary with trainees coming from various disciplines, including computer science, bioinformatics, computing and data sciences, electrical and computer engineering, neuroscience, and even physics. We also closely collaborate with various clinical experts listed below. I have kind of color coded each of their expertise because it's important to highlight that the lessons that we are learning are coming after talking with various people who are seeing, medical data and dealing with patients in completely different ways. This truly informs us on how to really think about solving the clinical needs or the current needs, and hopefully with AI. Um, Let me start with some background. Broadly, we are interested to build assistive tools for dementia. For those who are not fully familiar, I just want to give a quick background. Dementia is a very broad term used to describe cognitive dysfunction, and in fact, over 50 million people or more in this world actually suffer from this condition. And the numbers are actually growing pretty steadily. Um, Alzheimer's disease is a common cause of dementia, but there are many other ways somebody can get dementia. For example, um, someone with Parkinson's disease can get dementia, and somebody with vitamin deficiency can get dementia, or even somebody with depression can get dementia. So diagnosing the root cause of dementia is really challenging because it's not just about what level of cognitive impairment the person has, but one has to really understand and dig deeper to really identify those factors that are contributing to cognitive impairment. Um, as these cases, the dementia cases keep continue to rise, we are also facing another major challenge. Uh, and the challenge is that there are not simply enough specialists to manage these patients. Neurology is a very tough field, and let's be honest, not many people choose to become neurologists. In fact, I've spoken with several who have actually left the profession entirely. So now, we have these two issues colliding. One is the growing dementia crisis, and the other is this shrinking workforce to handle it. And the data is actually making it pretty clear, as you can see on this slide. This is a serious problem, and it's only getting worse. So that's why our team is kind of working on these AI-driven solutions to support clinicians. But we are not just building AI for the sake of it. We are developing these multimodal frameworks or models using real-world clinical data, including demographics, patient history, bedside cognitive exams, neuropsychological tests, neuroimaging, like MRIs and CTs. All these stuff is routinely collected in a clinical neurology setting. We are trying to take all that information in the raw data formats and then trying to build these multimodal approaches. So effectively, the goal is to put all these things together, trying to build these frameworks that are robust and resilient, and that can be hopefully be useful in a real world setting. Importantly, um, we are also putting a lot of effort in validation, comparing basically our model predictions with expert assessments, biomarker evidence, and even neuropathology. So the goal effectively is to not just create a powerful AI model, but to make sure that this can truly make a difference in clinical practice. So I want to now talk about what actually happens when a patient walks in a clinic. So today, how are these neurologists evaluating these patients today? So patient walks in a clinic, typically with a family member, with a chief complaint that is about the patient having some memory-related issues. The neurologist then gathers information such as, like I said before, demographics, patient level history, family history, medications, basically an interview process. And then during that process, the neurologist, administers some exams like physical exams, neurological exams, functional assessments, neuropsych testing or neuropsychological testing, and some other exams. Uh, and depending on the resources, they sometimes order an MRI or some other imaging. So with this kind of a multidisciplinary data, the neurologist has to now do the following, which is they evaluate the patient's condition, which is the cognitive status, whether have healthy cognition, mild cognitive impairment, or some sort of dementia, and then spend time to understand the underlying cause of dementia, which means is it due to Alzheimer's disease, is it due to depression, vitamin deficiency, and so on. And oftentimes it turns out that multiple factors are simultaneously contributing to the patient's condition, which means basically mixed dementia. So it's actually pretty complicated. Only experts can actually do this in a reasonable way. So this was really the problem that we wanted to work on. And for that, we started to collect a lot of data from multiple different cohorts, as you can see on the slide. And on each of these cohorts, there are multiple different participants, and the multimodality is basically, again, for each person, we are trying to collect demographics, their health histories, physical and neurological exams, imaging if available, and then trying to put all these pieces together. And we like to work with raw data. So all this data is actually coming in sort of this unformatted way. And we are trying to spend a lot of time to process this data, create pipelines, making sure all this data is actually then amenable for some kind of machine learning or AI based approaches. And this slide is basically showing our recent work that was published in Nature Medicine, where we collected data from multiple different cohorts that you can see on the right side, tens of thousands of participants, and we carefully curated all this data, processed all of it, made sure everything sort of really fits within the pipeline, and then we sort of started to think about these multimodal approaches. And the question we were asking was basically, again, going back to this differential diagnosis of dementia. And as you can see on the slide, there are multiple different categories listed on the left side. Again, going in line with the workflow of the neurologist, where the first thing we're doing is we're trying to assess if the person has healthy cognition, mild cognitive impairment, or dementia. And if the person has some sort of cognitive impairment, then we are going down to list and understand all these different factors that are contributing to dementia. And these things that you're seeing here, which are about 10 different etiologies of dementia, starting from Alzheimer's, Lewy body dementia, which includes Parkinson's disease, vascular dementia includes things related to vascular conditions, including stroke, prion disease, which is a rare condition. Frontotemporal degeneration is again a very broad category, but we are listing that as one etiology here. Normal pressure hydrocephalus, which is again some sort of a rare condition. Systemic factors that include alcohol abuse, etc. Psychiatric conditions, including depression, and so on. So the idea is that if the model is able to sort of understand all these different categories in using this multimodal approach, we can then hopefully be able to provide a solution that can inline fit with the clinical workflow. And on the right side, you're seeing some performance metrics. This is just basically an overall performance of the multimodal approach to sort of really understand all these different conditions. And like I said before, it's not just the model development. We're also focused on validating the models. So I'm going to show you one slide, just really that kind of summarizes our result, which is a very exciting result. So what we did was we basically randomly selected about 100 cases or so. And on these 100 cases, we asked 12 neurologists to independently evaluate those patient conditions, given again the same multimodal data on each person. So, what each neurologist did was they took all those 100 cases and evaluated each person and then sort of listed what might be the cause of dementia as well as the state of cognitive impairment. And then we showed that on these randomly selected 100 cases or so, neurologist assessments augmented by our AI model exceeded the neurologist only evaluations by about 26% or so, and which was a pretty significant results because finally we were able to show that AI based solution is actually augmenting clinical practice, which I think was very, very exciting for us. And uh, this work again, like was published in Nature Medicine. It also got a lot of coverage in newspapers as well as in journals like Nature. So we were very excited about it because we finally believe we have a tool that hopefully can allow us to really think about translation. And with that, I just want to quickly summarize about the work that we've been doing over the years, although I only talked about this latest work that was published on differential diagnosis. We've kind of been working on this topic for many, many years now, trying to build those automated pipelines, starting all the way from tackling simpler questions, which are more sort of binary classification questions, but more focused on the method. But as we started to talk more with the clinicians, we realized that it's important to really focus on the clinical question, and sort of we evolved. And the science also evolved, and the methods are also also evolved. And finally, we are happy to say that we are able to now think of taking these tools and putting them in a clinical setting and then trying to do some validation in real time. So we are now partnering with a couple of clinical sites, one in Arizona and one in Illinois, to really think about how these tools can truly be assistive in hopefully a prospective setting. With that, I want to thank my sponsors. These are my funding agencies, and thank you for your time.